Okay, so you can see my screen. It's a little bit strange now.
I can see the screen with the, yeah.
Okay, anyway, yeah.
Okay. So I think Chris is going to also chair these sections. So we'll see.
All right, so we are live streaming. I can go ahead. We have 3 minutes. I can go ahead and let everyone in, or I can wait another minute or two.
I think either way is fine. We can just let people in first, so that I'm sure some people will be a little bit late or stuff like that. But we can start right now, I guess.
Sounds good. I will do that. Emma, if you would like to go ahead and start sharing your screen, then we can be ready when in about a minute.
Hi, Emma.
Hello. Good to see you.
Likewise, likewise. Great. So Emma, I'll give you a heads up around 25 minutes. And if it looks like you're getting to the end, I'll let you get to the end. But if it looks like one needs to step in, well, okay.
Sounds good. Yeah, my last couple slides I can go fast or slow through them. So
that's good. Sounds good. Okay, Steve, shall I just? I'll of course handle this session.
Yeah, thank you.
Cool. Okay, I guess we're pretty much at 2:30 Eastern, according to my watch here. So welcome back, everybody, to this the continuing sessions on mechanical and civil engineering at MLSE. We have a great continuing great session for this one. And it's my pleasure to get us kicked off by welcoming Emma Lejeune from Boston University. And Emma is going to be talking about benchmark data sets. So all yours.
Yeah. All right. Thank you very much, Krishna. And hello, everybody. My name is Emma Lejeune, and I'm an assistant professor in mechanical engineering at Boston University. So greetings from Boston. In this talk, I'm going to discuss some of the recent work that we've been doing on constructing metamodels of heterogeneous material deformation. And I'll begin with a brief introduction, then I'll introduce mechanical MNIST, which is a benchmark data set for mechanical metamodels that we've been working on. And then I'll give 2 examples of some of the work that we've done recently on overcoming expensive training data and then overcoming limited information. And then I'll wrap things up. So in my work, I'm really interested in simulating biological materials, especially biological tissue. And one of the major challenges in doing this is that biological and also bio-inspired materials are spatially heterogeneous. And we can see some examples of this on the slide. And just very broadly speaking, modeling heterogeneous materials is challenging in part because of the massive input parameter space. So for a certain block of material, there are just so many potential different material property configurations that are possible. And often to get a true picture of the range of possible behavior, we'll need to run multiple simulations. And this can be really limiting when a single simulation takes a long time to run and the input parameter space is essentially so big that we need several thousands of simulations to fully explore it. So this brings us to metamodels, or models of models, that are essentially constructed by training a machine learning model on a database of simulation results. And this practice will essentially allow us to take model inputs. So in all the examples in this talk, it's basically going to be material property distributions that look like images or these bitmaps, and then use a machine learning based method to predict fixed quantities of interest. And ultimately, once these models are trained, they'll run at a fraction of the computational cost of running a whole finite element simulation. And we've seen a lot of really great examples of what this is useful for earlier today. Just sort of to highlight some examples from the literature, this really becomes an essential tool when you want to do anything that requires a high number of simulation runs or requires you to operate really quickly or make predictions based on multiple data sources. So just kind of methodologically, there are examples in multi-fidelity modeling, material design optimization, uncertainty quantification and sensitivity analysis, real-time prediction, data integration, and more. Like I said, this slide just shows a few nice recent examples of using machine learning to construct meta models. However, really, despite all of this recent work, there isn't necessarily a clear picture of what types or architectures of meta models will work best on engineering mechanics relevant data. So on this slide alone, I've drawn little schematics of feed-forward neural networks, variational autoencoders, convolutional neural networks, and then there are just so many different potential methods that aren't illustrated here. And within kind of each one of these potential methods, there are also different architectures to choose from, different options for hyperparameters. There's just such a large kind of design space for these meta models themselves. And for someone like me who wants to kind of understand better what types of meta models to use to solve the problems that I'm interested in, I really don't necessarily know what the best choices are. So one potential way to overcome this is to look at what's been going on in other fields, specifically computer vision, where benchmark data sets have just had a massive impact in demonstrating the efficacy of new methods and then also motivating new directions for research. So two of the most popular examples are shown on this slide, ImageNet, a collection of labeled images, and MNIST, a collection of labeled handwritten digits. And I just want to point out that the barrier to entry for working with these data sets is super low. You can download MNIST in 2 lines of code. You could do that now, kind of before I get to the next slide. And having these data sets at our fingertips really make it easy to compare different machine learning models by evaluating their benchmark performance. And in this talk, I'm going to show some of my very early attempts at creating something similar for mechanics problems, and specifically kind of within that benchmark data sets to simulate heterogeneous material behavior. And I'll just provide a snapshot of what I've been working on with that, and then some of the problems we've looked at with these benchmark data sets so far. So this slide kind of summarizes the mechanical MNIST benchmark data set. It's a data set for regression problems in mechanics. And obviously, as you can tell, we're directly inspired by the original MNIST data set of handwritten digits. Just kind of as an aside, we chose to do this because the original data set is very well known, but perhaps more importantly than that, it's also a really nice size. So it's small enough to download really on any modern computer with a standard Wi-Fi connection, but it's also large enough to meaningfully train a neural network, especially a convolutional neural network, which is a really important method for this type of problems. So what we do here is we convert 70,000 images to 70,000 simulations of a neo-Hookean material with a varying modulus, where the digit is essentially a high modulus material embedded in a low modulus matrix. And then we run simulations where we deform the block of the material. And you can see in the examples here, you have the stiff digit, and it influences how the entire domain deforms. And then for each 28 by 28 input bitmap, we have full field displacements, total change in strain energy, and then total reaction force at multiple steps of applied displacement. And I'll just note briefly that we conduct all these simulations with the open source library Phoenix. All of our code is available on GitHub, and I'll share the links to download this data set later in the talk. And it's my sincere hope that people will download it and try out some of these methods or whatever methods you're currently interested in. So the mechanical MNIST data set also contains multiple different load cases illustrated in this upper row here. We also have added in recently the fashion MNIST pattern, which is kind of, at least as a classification problem, it's more challenging. For regression problems, maybe it's not necessarily more challenging, but it gives us a little bit of kind of diversity in what we're evaluating our meta models on. And then we also have multiple different simulation fidelity levels. So in the final row, I show a full fidelity 2-dimensional simulation, some low fidelity 2-dimensional simulations that use coarse meshes with linear elements, perturbation simulations that apply only a fraction of the total applied displacement, and then a final 3D example that would be a high fidelity simulation. And in this talk, I'm going to focus mostly on the uniaxial extension load case for the MNIST pattern of digits. So we're going to focus specifically on meta models where we predict change in strain energy at the end of the simulation from the original input bitmap. But I'm also going to further validate the results that I show on the fashion MNIST data set. And then also we'll draw from these additional simulation fidelities in part of the talk. So first and foremost, we can train a convolutional neural network to predict strain energy at a fixed applied displacement from an initial input bitmap. And from this graph, where we plot mean absolute % test error on the y-axis and then number of training samples on the x-axis, you can see that when we get excellent performance of our meta model, when there are tens of thousands or so of available training examples, which is that's not surprising, essentially, given what's known about convolutional neural networks. Of course, when there are only hundreds or say 1,000 training examples, the meta model performance is not great. And we're really in this region where we'd want to be able to add more training data. And essentially, the problem is that for a lot of the problems that we're interested in with modeling spatially heterogeneous materials, we're actually more often really in this area where we want more training data rather than in this region of diminishing returns. And that's kind of for two main reasons, and potentially more, but two main reasons that I've identified on this slide. So one problem might be that the simulations themselves are too computationally expensive or require too much human intervention to run tens of thousands of them. And then the second problem is that we might have limited access to input bitmaps or spatially heterogeneous material property distributions. So in the context of this toy problem with the mechanical MNIST dataset, we might only have, say, 1,000 examples of handwritten digits to use as simulation inputs. So in the next two sections of my talk, I'm going to address some of the methods that we've tried out to try and overcome these two problems. So the first problem is essentially that generating training data can be prohibitively expensive. So with our toy problem with mechanical MNIST, we're able to generate enough simulations to reach this point of diminishing returns. But in the real world, our best case scenario might only be around 1,000 simulations that are possible, especially if each simulation is something like what's pictured on this slide, like a whole organ simulation. And also especially if each simulation is going to require even just the tiniest bit of human intervention to just do a sanity check and ensure that it's correct. So then the question is, can we leverage low fidelity data sets to make predictions with our meta models, in particular convolutional neural networks, and basically move further down this curve without running more full fidelity simulations? And I'll say that there has been a lot of recent work in this direction. It's often referred to as multi-fidelity modeling. Here I'm going to use just the broader term transfer learning, which describes the practice of leveraging the knowledge gain while solving one problem. So in this case, the first example we're going to talk about is using a low fidelity simulation to solve a different but related problem. And in this case, the different but related problem would be a high fidelity simulation. And on this slide is an example of what that might mean in the context of problems in computational mechanics. So in a toy problem where we're simulating the deflection of a heterogeneous beam, a low fidelity simulation might be a simulation that has linear elements and an unrefined mesh. And maybe what we really want is an incompressible beam, but instead we choose a lower Poisson's ratio. And then a high fidelity simulation would be a more expensive, but obviously more accurate element selection with a fully refined mesh. So these low fidelity simulation results are kind of going to be terrible. But with transfer learning, we can pre-train our meta models using the low fidelity data and essentially get better performance after transfer to the high fidelity simulations with many fewer high fidelity data points required. And so in the context of our toy problem with the mechanical MNIST data set, here's what the different simulation fidelities actually look like. So on the upper row, we have our high fidelity simulations. So we have fully refined meshes, quadratic elements. We threw in a 3D example. And then on the lower row, we have meshes of various coarseness with linear elements, and then simulations where the applied displacement is just a tiny perturbation that's a tiny fraction of the displacement in our full fidelity simulations. And you can see that simulation times here range from fractions of a second for our perturbation simulations on the coarse mesh to tens of minutes or so for our 3D simulations. And all these simulations are conducted with Phoenix, which is not necessarily the fastest code, but the important part is essentially that the high fidelity simulations can be orders of magnitude more expensive to run than these low fidelity simulations. And then on this slide, we show a schematic for how we're going to conduct transfer learning. So essentially, we'll use one of the absolute simplest forms of transfer learning. So model pre-training, where we simply train our model on one data set and then use that as the initial conditions for further training on the actual data set that we care about. And you can see that in PyTorch, this can be implemented in one line of code. It's very straightforward. So that was kind of our starting point for what we wanted to look at for trying to leverage this low fidelity data. And really the thing that's kind of cool is that despite being pretty straightforward, it's a pretty effective technique. So here we use our coarse mesh perturbation simulations as our low fidelity data to pre-train the model. And then we perform additional training with our high fidelity data set, so uniaxial extension, fully refined mesh, quadratic elements. And this plot basically shows the test error on the y-axis and the number of high fidelity simulations used for training on the x-axis. And the black curve shows what it would look like with no pre-training. And then each one of the other curves shows a different number of low fidelity samples used for pre-training. And you can see with the point that's circled in blue, where we have just 100 high fidelity simulations, we can achieve a comparable test error to the meta model that's trained with 60,000 full fidelity simulations. And this is cool, or at least it was very cool to me, because even with this toy problem, running 60,000 high fidelity simulations will definitely require some sort of supercomputer. And in this case, the combination of 60,000 low fidelity simulations and 100 high fidelity simulations is something that you could just hypothetically generate overnight on your laptop. And we also show that these results hold up with the fashion MNIST dataset. So in this case, the full fidelity best case scenario gives us 2.8% test error, whereas the transfer learning based approach is 3.6% test error. And you can see that there's substantial improvement over this black curve with no pre-training. And basically, you can also see that the fashion MNIST problem is a little bit more challenging. So with the really low levels of training data, your performance is much poorer than on the original mechanical MNIST data set. And maybe just a little bit of intuition for why this practice is so effective. We can use guided backpropagation to essentially visualize what the convolutional layers of the neural network are seeing when they look at an input pattern. And in the upper row, we show a meta model trained with 100 points and a meta model trained with 60,000 points. And then in the lower row, we show a meta model pre-trained with 60,000 low fidelity data points and then transferred to the high fidelity data set. And we can see that just kind of qualitatively, all of the models trained with the higher number of data points are much more similar than the examples with just 100 training points. So the pre-training process essentially helps us access this form in a pretty dramatic way. And then we show a couple more examples where what we do now is we transfer between load cases. So the first example on the left, we go from uniaxial extension to equibiaxial extension. And this isn't necessarily a transfer between fidelities. We just kind of wanted to see what would happen. And you can see that the transfer is a little bit less effective than the previous example, But the model pre-training still gives us a boost. It just maybe takes, say, like 1,000 of the simulations that you're actually interested in to capture kind of that full performance. And then we also show a highly effective example where we go from a perturbation simulation to these 3D simulations. So here at the circled blue dot, the meta model is trained with 100 high fidelity simulations and 60,000 low fidelity simulations, and it's performing just as well as the meta model trained with 60,000 full fidelity simulations, which is pretty nice, given that the low fidelity simulations are dramatically cheaper. And on this slide, we show the actual data from these same examples, so equibiaxial extension and uniaxial extension, and then 3D extension and twist and the 2D perturbation. And we see that for the more effective case of transfer learning, the data is more correlated, which isn't surprising. So the neural network really just has to learn this relationship. And then kind of zooming back out to the big picture, to overcome this problem that running tens of thousands of simulations is unrealistic, we can use transfer learning where we pre-train with correlated low fidelity simulations to overcome this. And this is interesting because it means that there is kind of at least it kind of changed maybe the way I think about generating training data for these types of simulations. So there's sort of a new ideological challenge of deciding what the correlated low fidelity simulation should actually be. And then the nice thing about this approach is that we have a massive flexibility and kind of a room to be creative in designing effective low fidelity simulations, because they just have to be kind of correlated to what you're actually interested in. So then the second problem that I mentioned, which is that even if we can now leverage low fidelity data, we might not have enough examples of a heterogeneous pattern that we're actually interested in to do this. Again, a real world, a best case scenario, we might only have fewer than 1,000 or so input parameters. Here's an example of what that might look like when input patterns are collected from, say, a histology slice, if we're interested in problems in biomechanics. And if we go back to our kind of mechanical MNIST problems, the question would be, how can we access this lower part of the curve if we only have 1,000 examples of what the input pattern might actually look like? And I think there are points here that are super related to the talk we heard, the really nice talk we heard earlier from Assad. So a very kind of naive option would be to generate more input patterns to run through a finite element simulation and then train our model, would be to just start with these randomly generated input patterns where we shuffle the pixels of the input distribution, essentially in an uncorrelated manner, choosing a pixel brightness at each location that's drawn from the distribution of the images that you have as examples. And we can try this and we can basically say, okay, it might artificially lower test error at the start, where test error is computed on the real pattern. But as we add a significant number of these randomly shuffled patterns, the performance of the model actually ends up degrading. And you can see that in the dashed red line there. And then if we actually open up our model and visualize a projection of one of the final fully connected layers, so in this example, we use UMAP to make that projection, where you have a high dimensional space that's just visualized in 2D, we see that the model is actually separating the real data from the generated data. So it's effectively learning the difference between the two types of data as it makes predictions, and this naive approach clearly doesn't work. So I'll go through this a little bit quickly just in the interest of time, but our second option is a bit more sophisticated. So we can use some sort of generative model or a model that generates new instances of data. So in this case, new input bitmaps to then run through our finite element simulations to generate more training data. And specifically, we can use a variational autoencoder that's illustrated right here, where a network is trained so that the input data can be encoded into a lower dimensional latent space that can be then used to approximately recreate the original inputs by passing it through a decoder network. And once this network is trained, we can draw random samples from the latent space and then run them through the decoder network to generate new input data. And this is what it would look like essentially for a 5-dimensional latent space trained on the MNIST input pattern. So these input bitmaps. And the points here illustrate the latent space, and then the samples here show generated samples where 100, 1,000, and then 60,000 points are used to train the variational autoencoder network. And the generative model will basically allow us to augment the training data set with finite element simulations that are based on these generated patterns, right? So they don't have to be perfect. They don't have to be labeled in any way because we're going to label them by running them through our finite element simulations. And this slide is basically just for fun. Even though we were talking about just a toy problem in this talk, the mechanical MNIST data set, this approach will also work for more relevant patterns. So this is just an example with Cahn-Hilliard patterns, a projection of the latent space, and then some examples of generated samples for these patterns. But so we try it and we train a convolutional neural network with a mixture of these real and autoencoder generated samples, and it doesn't work essentially. So the test error is actually worse here than when we trained with the random patterns. And when we open up our convolutional neural network and look inside, you can see that there really isn't great integration between the real and generated points. So the real points are quite concentrated in the model's latent space. And just kind of, we want to try and fix this. And one of the criticisms of autoencoders is they tend to produce somewhat blurry patterns. So in our case, where we treat the brightness as stiffness, that is potentially a major source of why these two data sets are quite different. So just very briefly, we can create a sharpening filter that will adjust the brightness of the generated data to match the real bitmap samples. And this is just an example of what this actually looks like. And then finally, when we run this through our model, the augmented data actually starts to help. And the augmented data decreases test error. When we visualize the latent space, we see a nice integration between the real and generated data. And then when we look at the performance, so this shows the performance on the low fidelity data set when the augmented low fidelity data set is transferred to the high fidelity data set with 1,000 examples. So basically combining the methods we talked about earlier, the test error ends up being 2%. And this holds up with the fashion MNIST data set as well. You can see that the latent space of these two data sets looks quite different. And with the fashion MNIST data set, when we transfer the high fidelity data set, we actually get really lucky and beat the performance of the original transfer learning approach with our generated data. So in conclusion, even though we can effectively train convolutional neural nets on our toy data set just fine, we anticipate essentially two real-world problems that will prevent the broader adoption of convolutional neural network-based metamodels. First, the high computational costs of generating enough training data, and the second would be limited information about the range of potential input material property distributions. And we can make progress with this combination of transfer learning and generative models. And if you follow this QR code or this link, or I think it's also posted in the abstract of the talk, you can download this data set and try these methods out yourself or other methods and see if you can beat the performance that's shown here. And just very briefly, I wanted to talk a little bit about some outlook. This will just be one more minute. So if we look inside our convolutional neural network that we have right here, and we look at the latent space for the input pattern and then the latent space for the model, you can count basically 10 clusters here. This model is really just memorizing a pattern. And I think that one thing that'll be really interesting to look at going forward is this sort of option of reconfiguring our meta model so it interacts with more of the data that we're spitting out when we run our finite element simulations to kind of change what the model actually ends up seeing. And this is an example here of a network that's trained to first predict displacements and then predict change in strain energy. And right now, this model has worse performance than our previous model, but you can see by looking at these latent spaces that we kind of change what the model sees. And then this is just an advertisement for one data set that we've worked on, a classification problem in mechanics. And then this is another advertisement for a data set that we've worked on with our collaborators at UT Austin. In their lab, they generated this really nice experimental data set that would be really useful for anyone interested in validating data-driven constitutive models of soft tissue. And that's it. Thanks very much for listening.
Thanks very much, Emma. That's pretty important and almost pioneering type of step that you're taking here. So very cool. So we have a couple of questions here. Let me start out with the first one. With regard to this approach to transfer learning, how do you identify what aspects of the model you need to are best transferable between the low fidelity and high fidelity?
So the approach that we have used so far here is just like such a naive approach to this. Like it's the simplest approach I can really think of, where we just pre-train our entire network on the low fidelity data first. And that basically gives the network a major boost when you start, when you switch to the high fidelity data. It would be really interesting to take a different approach to this problem, where you basically use the low fidelity data to do some sort of feature construction, and then subsequently pick that up and train that on high fidelity data. But I haven't tried it, but I'm sure we could learn a lot. Or yeah.
So sort of related to that, have you found it important to include some aspects of the physics, in addition to just letting it run with the data? So something that we found, for instance, was that, right, if you train, for instance, for the free energy, or for the strain energy, right, but then you're interested ultimately in the stress strain response. You do need to, of course, these models do better as you teach it something about the physics. So yeah, I mean, definitely in the context of multi-scale modeling or something like that, where you would care about the derivatives and then the derivatives of the derivatives of the strain energy function. I think that if you wanted to successfully incorporate that into this framework, I think that is basically absolutely necessary. For just predicting a quantity of interest, at least with the patterns that I've tried, these straightforward approaches work really well. But you can see I went back to this slide, it's definitely not learning any mechanics. It's just memorizing this pattern. And that's kind of why I'm interested in seeing if there's a way to force these algorithms to learn a little bit more mechanics by kind of forcing more data at them.
Can I ask one question? Do we still have time?
Yeah, absolutely. Go for it.
I just don't want to type, so I'm wondering. So I'm wondering, for the data of different type, have you think about how to organizing it? Maybe have a hierarchical structure, or maybe have a graph structure to organize different type of data so that we can facilitate that for transfer learning?
Yeah, so I think that my goal for the next month is to learn more about graphs. And I think that there's a really high chance that if some of those methods were even used on the same data set, you would end up with a lower performance, or a better performance, a lower error. I haven't tried that yet, though.
Thank you.
Cool. Excellent. Thanks so much, Emma. We're right on time, and that brings us to our next talk by JS Chen from UCLA. It's all set. Deep autoencoders for physics-constrained twins of musculoskeletal systems. Fantastic, JS. Great. All looking forward to it.
Thank you, Krishna. So I'd like to share with you our recent research in the topic that Krishna just mentioned. The work is really done by my student, Xiaolong He and Karen Tajana, in cooperation with Kaichi He at the PNNL. Okay, and so as a motivation of this work, okay, so we are interested in developing digital twins for various purposes. One will be for rehabilitation for soldiers and athletes, for example, hamstrings injury, elbow injury, and things like that, for early detection of those problems, and then for rehabilitation for elderlies, atrophies and things like that. Okay, so as you can see now, this really have to get down to a smaller scale to understand the physiology side of how muscle functions. But then to relate to the muscle functionalities, that you have to now link that to component scale, if you will, and structural scales. Now, obviously, there are many data that can be collected. And if this is supposed to be a digital twins, well, this will now have to be patient specific, right? So everything has to come from images, for example, MRI and DTI, which is the diffusion tensor images that gives you the water molecules in the muscle tissues, and that gives you the indication of fiber, muscle fiber orientation, things like that. You also need to know the material properties that can be tested in the laboratory, and get stress and strains and so on. The continuum scale, these days the wearable sensors are very popular and has advanced to the level that we can collect a lot of data that allows us to understand the kinematics and kinetics of how muscle functions at this component scale. Now, the structural scales, same thing here with wearable sensors, with motion tractors. We collect a lot of information. So now the question is how do we go from left to right to then muscle physiologies and to identify the potential problems in the muscle systems. Now, from cellular scale to continuum scale, a lot of data are really in very high dimensional space. In our previous work, we have introduced the manifold learning. Combine that with the reduced order approach, and we'll be able to correlate the information from cellular scale to the continuum scale. But as you mentioned, this computation cost is quite high because of the very high dimensional space that all this data lives in. Well, from the continuum scale to structure scale or whole body scales, one will have to solve either forward or inverse dynamic problems. So this involves, again, parameter identification, and one can use, physics constrained neural network, recurrent neural network, and so on. But still, all these problems involve extremely high dimensional data space. So in this work, we will further introduce autoencoders and see how this can be then combined with physics laws that we understood to better solve the problems. Okay, so just a brief introduction of deep autoencoders. Basically, this is one of the manifold learning techniques. It's essentially a data compression, very similar to wavelets or multi-resolution type of techniques. So you have the input data here that can live in the extremely high dimension. And so, for example, like this demonstration case at the bottom, the data also usually have a lot of noise, and there are some outliers. And what you can do is to construct some neural network architectures, and it allows you to do a data compression and basically project this data to low dimensional space. It's called embedding space. This is where you have a lot of freedoms here to operate on the data because they are in an extremely low dimensional manifold. It also has the ability to filter out noise, some of the unwanted noises and outliers. Then what you can do is once you get the information you need from here, you can then reconstruct the data back to the high dimensional space to get the proper data that you need. Right? So obviously the objective here is to have the output to be as close as to the input as you want. On the top of that, as I mentioned, there are some physics laws that we already have in hand. So how do we combine this to do a more effective data-driven computing? So as I mentioned earlier, we have done some work before on manifold learning. And so how does this compare to the earlier work? And so, for example, if you have a data right here that live in very high dimensional space, this earlier work on manifold learning is that you pick up physics laws and you get some, for example, stress and strain states that are on this space. Now you try to relate to the data set that's also extremely in high dimension. And so what you do is you do a local data reconstruction and project the high dimensional data onto a low dimensional manifold. And then from there, you search for the closest point of the data that is consistent with the physics laws you have in hand. And then you do the iteration until the solution converges. Now, the downside of this is that everything is done online, right? So as you can imagine, even when you do the projection, you do the local data reconstruction, and we have introduced this coercivity type of local data construction to enhance the stability. But still, all these operations are done online. So the idea here is to use the available techniques such as autoencoders and train the data. And so if you have sufficient data, then a lot of the training, the encoder, and encoders and decoders can both be trained offline. And really all you have to do here is try to relate the physics data of physical states to the material states through encoders and decoders, and make sure that they live in convex manifold to ensure the stability of the computation. So this is what we're trying to do here. Okay, so now get back to the mesoscale. As I mentioned earlier, this is all patient specific. So everything comes from images and data available at each pixel point. Okay, so here is just some examples of the cross-sectional images taken from MRI. Now you can then stack all these images together, and with some segmentation techniques, you can identify pixel points for muscles, pixel points for fat, and for connective tissues. Now we also have the data from DTI, the diffusion tensor images that provides you the information at every pixel point, the water molecular motion, and that gives you the fiber orientation, the muscle fiber orientation, which is also very important at every pixel point for us to do data-driven computing, right? So now we have to deal with this. So to deal with physics laws, everything now, all the information stores in the data sets, in the pixels. So it's more convenient here that we use methods such as reproducing kernel as approximation function, to construct approximation functions to solve for the solution of the physics laws. The nice thing about reproducing kernel is you can control the locality of the functions, and that provides you the choice of collecting the data from the nearest neighbors. And for data reconstruction, this is also very important to have these kind of capabilities. There's also a flexibility in controlling the smoothness of the kernel functions. So for example, solving equilibrium equations, you would like to use a function that is smoother. But when you then search for the data from the physical state, that you would like to use a rough function because it allows you to relate to the discrete data that is generally very rough. Okay, so now the framework looks like this. Suppose we have the physics laws that we have in hand. In this case, will be kinematic and admissible stress field that is satisfied, for example, equilibrium and traction boundary conditions. And then you have compatibility that relates strength to displacement field with essential boundary conditions. So then you define the kinetically admissible stress field and kinematically admissible displacement field. And let's call this physical manifold. Now to relate equilibrium to compatibility, you often, in the conventional computational mechanics, you rely on the stress-strain relationship, usually come from phenomenological laws. Here, due to the complexity of the problem, the stress and strain information will come directly from data. And let's call this material set manifold. So the objective here is to look for the solution that are on the intersection of this physics manifold and data set. Okay, so you can formulate this by a minimization problem where you define some distance function now that measure the physical stress and strain and material stress and strain. And by the way, I'm using a notation that with heads are the strain and stress data sets. And the one without heads are the physical states that are computed from equilibrium and comparability. Now, of course, you can minimize this distance function now by an iterative procedure. Given, for example, a stress strain data set, you search for the physical stress strain pair that minimizes this function now, or vice versa. So you can recast this minimization problem as a two-step minimization. At the global step, you minimize this distance function now by given the material data set. And then you have this argument, then you minimize that argument by searching for the local stress strain data from the available material data set. Okay, so let's go back to the physical state. Again, I'm minimizing this distance function now, subjected to equilibrium and the corresponding boundary conditions. Of course, you can set up this function now that treat these two conditions by the Lagrange multipliers. You go through the standard procedures, you get three set of equations. The first equation here can be viewed as a generalized equilibrium. The second equation here, as you can see on the right-hand side, I have the material data set, the strain data, and I can then relate that to physical strain. The third equation allows you to relate the stress data to the physical stress field through Lagrange multiplier. So how do you choose approximation functions? In the first generalized equilibrium equation, obviously the solution is smooth to satisfy equilibrium, and therefore the test space for this Lagrange multiplier will have to be smooth. In the second equation, we start to relate the strain data to the physical strain through displacement field. Now the displacement still need to satisfy equilibrium. So therefore here you can still use some smooth functions, although this smoothness can be less than what you have in the Lagrange multiplier. The third equation here allows you to relate the experimental stress data to the physical stress. So therefore here you will choose this test function as a rough function. So this is how we construct those three approximation functions. For the displacement field, we use reproducing kernel with C0 continuity. Same as the Lagrange multiplier because it played the same role of displacement field. And then for the stress field, we use this indicator function, which is basically a piecewise constant function, because that allows us to match the experimental stress state to the physical stress state. Okay, so now then you solve the first set of equation that relates experimental strain field to the physical displacement field. And to avoid taking any derivatives on the data, then we use contour integral to compute the gradient. And to also avoid any numerical instability, that we use this stabilized conforming nodal integration with nodal data directly taken from the pixel points. The second equation is a generalized equilibrium that we have mentioned earlier. And the third equation allows you to relate the experimental stress data to the physical stress data through Lagrange multiplier. So here we'll use the indicator function, which allows you to do a direct collocation on this projection, right? So then you can bring the third equation back to the second equation through the experimental stress data. You then compute Lagrange multiplier, come back to the third equation with the experimental stress data and the Lagrange multiplier. You then update the physical stress state. That's to satisfy the equilibrium. Okay, so that's the global step. Now coming down to the local step. Once you have the global step, which is the physical stress and strain calculated, instead of then from there to search for the data that lives in the very high dimensional space, now we have this encoder that will then project the stress and strain states onto the embedding space that lives in the very low dimensional manifold. Okay, so then locally, then we do the search of the nearest number. Then we do the local data reconstruction to construct a local convex hull. And then from there, then we project the data back to the high dimensional data space. You can do this in various ways. You can do now with the decoder and map it back to the high dimensional stress strain data. Or you can actually, from here, when you do the data reconstruction, directly use the high dimensional stress strain data to construct the convex hull. And then you can get directly the projection onto the convex hull to get the experimental stress strain data directly. Okay, so how do we construct the local convex hull? We can actually get back to the reproducing kernel. We will use the kernel function, which is a positive function. So for example, the inverse distance function, and simply choose a constant basis that will then guarantee partitional unity. And partitional unity will guarantee the reconstructed data to be translational or rotational invariant. And then since this kernel function is positive, so this also preserves the convexity of the data reconstruction. So from here, you do the data reconstruction. So now this local reconstructed data as it lives in the local convex hull. All right, so with that, let's see how this method works. So here we take the material data where the testing is done by 11 protocols. 9 of the 11 protocols are the biaxial testing. And each protocol has a lot of stress strain data, so that the specimens are gradually pulled in 2 directions. And then the last 2 protocols are the pure shear testing protocols. So again, for each of the protocol, the many stress strain data. Now here we like to make a comparison on this data-driven computing, where the stress and strain data are taken directly from this measured data, compared to the case of the conventional materials modeling, where here we pick 2 constitutive laws. The one is the well-known Tong and YC-Fan model, and the second one is the Lee-Sachs model. And so we will then, for comparison purposes, if we use these 2 models, the material constants are then characterized through this experimental stress strain data, and then use this and combine that with equilibrium and compatibility and solve them by the conventional computational mechanics approach. Right? So let's see how these 2 methods compare. The reason we wanted to do data-driven computing and take stress and strain directly from the data is because, as you will see, quite often the phenomenological laws, when you do constants characterization, they typically work well on certain deformation modes, but it's hard to generalize those models to arbitrary deformation modes, and which you can see here exactly in this case. So here's an example that we take the pure shear test data, use one set of protocol for training and use the other one for prediction. And as you can see here, the 2 columns on the right-hand side are the prediction from the Fan model and Lee-Sachs model. And as you can see right here, they actually miss pretty bad in this case in the compression range. Now with this data-driven computing here, we use this locally convex data-driven approach. And as you can see, the prediction is actually much better than the case with the constitutive laws. Now, in this case, we now consider using more training protocols. So here we choose some training protocols that involve biaxial tension and simple shear. And then we try to do the prediction. And it is actually quite well known that some of the machine learning algorithms, they work well for interpolative type of prediction, but they don't work as well for extrapolative type of predictions, right? So here, the one in the figure in the middle are the type of prediction that are, the data is within, is more of interpolation. Whereas the curves on the right-hand side are for, the data is outside the range, the trending range, and they are more like extrapolation. And here again, we have comparison with the YC-FUN model. Well, if the prediction is within the range of the data, then you see that they both work well. Now, for the case on the right-hand side, on the other hand, this is more of an extrapolation. Well, the YC-FUN model, you see this, you start to see some error. For this data-driven computing, on the other hand, there are two cases of them that work better than the FUN model. But the one in the middle is actually worse than the FUN model, demonstrating that the earlier development of manifold learning doesn't do a very good job in terms of extrapolative type of prediction. So now let's compare to the one that we have introduced with the deep autoencoder. Okay, so this is the case with the interpolative type prediction. They work well. Okay, so this AEDD is this autoencoder data-driven computing, and this LCDD is our earlier work on locally convex data-driven computing. They both work well. Now you look at the extrapolated one, the locally convex data-driven computing. Now you start to see some deviation, especially at the large strand range. Here is the one with the autoencoder, and as you can see, it does a better job in terms of generalization of the data set from the local training and be able to extend to other deformation modes, even though they are extrapolation type of prediction. Okay, and same thing here. Now we look at the case where pure shear and biaxial tension are all considered. So you see a similar trend. For the one in the middle, the two columns in the middle are for interpolative type predictions, and the two on the right-hand side are for extrapolative type predictions. Again, the one at the bottom are the locally convex data-driven computing, and the one at the top is the newly proposed approach. And again, it shows enhancement of this approach. Okay, so now you can now, if we do we can now relate this, the cellular scale muscle behavior to continuum scale. Then what's left here is to go link from continuum scale muscle behavior to the performance of human body. And this work is still ongoing, so I'll just be brief. Now we're now introducing this recurrent neural network, basically to try to make a mapping between the measured motion, body motion, to the muscle fiber excitation functions. And this can be done, for example, by recurrent neural network. You can also enhance this with some physics constraint. Right, so these are some preliminary results on some training and prediction, data. We can also consider PIN, physics-informed data, a neural network, and for solving the inverse dynamic problems. And this work is still in progress, but the combination of this will hopefully allow us to use the motion data and do an early detection of potential either muscle injuries or muscle diseases. Okay, so with this, I conclude this talk. We have introduced this auto-embedded data-driven computing as an enhancement of the earlier work on manifold learning. And the method works quite well in terms of generalization of the training data, from the training data. We have also introduced is reproducing kernel that turns out to be quite flexible in terms of using it for solving physics constraint equations and for data reconstruction to construct the local convex hull to enhance the stability of the computation. And this is a collaboration with the Navy, a medical research center, try to use the motion tracking machine and be able to identify the potential muscle functionalities. Okay, so with this, I conclude my talk. Thank you very much. And just finally, just show an advertisement that winner already shown. Thank you.
Thanks very much, Yes. That's really interesting work. The floor is open for questions, and maybe I can take the opportunity to start here. So with some of the earlier parts of the talk where you were showing structural mechanics models, can this be viewed as a generalization of classical PD constrained optimization, where you're not, sometimes in those problems you may use only displacement data, but here you're using more, you're using more generalized data, you're using stress and strain, and that also leads to the the sort of multi-field, the connections to multi-field variational problems also.
Right. So that's why you need to be careful about elasticity, because as you know, multi-field variational principles, you get into the saddle point problem, you have to have in-soup conditions and all that. And that's why in this we pay a lot of attention on constructing this convex hull and making sure that the approximation functions are lives in the has the elasticity to guarantee the stability of the solution. In this case, is multi-field variational principle, but coupled with the stress strength data. So it needs to be done not only to make sure that you have coercivity, but also making sure that when you search for the data, that convexity is also there. And this is particularly sensitive exactly because of the multi-field approach that is taken in the physics laws.
I see. Oh, sorry, go ahead.
Can I also ask questions about the data-driven parts? Sorry, I just don't want to type it. So I was wondering, for the local minimization problem, if after solving the local search, the distance is still very wide, what would you suggest, JS? Should you try to generate new data, or should you try to going back to a model-based approach, or what would be the strategy?
So to search for data, the most straightforward way, in which Michael Ortiz and his co-workers have done, with the minimization of distance between the physical data and material data. That's what they had done earlier, but it turns out to be the results could be sensitive to the noise and outliers of the data. That's why here we use this local data reconstruction, which is actually, the idea came from the embedding theory of machine learning, where it serves as a noise filter. And that way, then and when you do the projection, you project to the local convex hull. That gives you a
see. So in your case, you already constitute a local metaphor that actually can have. Okay.
Great. Thanks, Jess. That brings us exactly to the top of the half hour, and we're on to our third talk of this session, given by our lead host and our main organizer, Steve Sun, meta modeling for plasticity. Great, Steve, all yours.
So Chris, I think we are both share, maybe you are the main one since you're more senior.
Okay. Sure.
So thank you, everyone. So today I'd like to talk a little bit about our recent work on using neural network to write a plasticity model. So this work is actually done mainly by our PhD student in my research group, in particular Nicholas, who actually worked on the level set and geometric learning, and my previous student, Kun Wong, working on the model validations, and also Bajado that are working on the Model 3 Pro mechanics, and then my two postdocs, one work on the Lie group mapping, and another one working on FFT simulations. The motivation behind writing the parasiticity model with neural network is the following. In general, the discovery of new mechanism from the data require a lot of back and forth and deviations. We can see from the history of parasiticity model from the Juker-Prager to J2 parasiticity, it takes 40 years. And then we have the critical stage soil parasiticity in the 60s. And in 2004, we have the fiber cancer. If you think about the mechanism of that discovery, a lot of them are due to new relation discovered by different physical variable, but it also on finding different way to represent the relationship of a parasiticity model. So we can see that from Mises to Juker-Prager to Gersons to Mock-Coulomb, we can think about it not only as a physical problem, but as a geometry problem. In particular, how do we generate new yield functions and new shape? And then how do we evolve that yield functions in the principal stress space in order to solve the problem? So there are some previous work already in that directions. In particular, in UK, in Durham, there's a work on using the NURBS to generate arbitrary yield surface on the principal stress space or in other stress space that can actually use to personalize or customize yield surface. But then the drawback of this method is that it only works for perfect parasiticity, because in order to actually replicate the parasiticity model, we need to have hardening and softening. And that means that the geometrical objects that are in the principal stress space to yield stress is not a fixed entity, but are evolving over time. So in our research group, we have done some previous work in which we introduce a decision tree and then use reinforcement learning to guess what is the best combinations of the yield surface hardening model, and then actually find out the optimal parameter or the strategy, including neural network method, to actually determine the best performing model. The drawback of this approach, however, is that you need to hard code all the possibility in the decision tree, and it makes it very difficult to discover new pattern that we don't have knowledge. For example, if there are a new yield surface that we never know the shape of it, we were never able to replicate it in this in this decision tree method. So that motivates us to the other extreme, in which case we will use neural network to make predictions. And the neural network offers a lot of flexibility and also a lot of choice, not only in terms of the hyperparameter, but on the type of neural network that can achieve the same path dependency. Shown here is just 3 different types of method we have used. We can use the recurrent neural network, the gated recurrent neural network, the multi-step feed-forward network, or the recurrent network. The drawback, however, is quite obvious in the sense that it's really hard to actually analyze how does this model fulfill the physics constraint. For one simple reason, we don't have a partitions of the elastic and the plastic string. We don't have any geometrical interpretation that help us analyzing whether this is actually fulfill some thermodynamic law. And we basically get a black box model that without the machinery. So the goal of this research is to see whether we can find the sweet spot where we can actually introduce enough details in the constitutive law, but yet have enough flexibility in the parametric space so that we can generate any arbitrary parasiticity model. So this is actually, so this talk is about the construction of the model that not only fixed in one particular data set, but for different data set, we can automatically generate different parasiticity law that are actually designed for different data. So this is actually one example of the plasticity data in which we have two different microstructure, and then we can, as we can see that we can generate different U surface based on the microstructure, and that would be the goal of this talk, is to provide the details. The first step is actually a very classical plasticity problem. What we want to do is actually to identify the initial U surface. I'm not going to go too much about the detail. Basically, it involves visiting different stress, generate different data point in the stress space, and then we identify what is the initial yielding point, and then come up with the machine learning algorithm that generate the yield functions. The same technique can be applied for elasticity, and so that we can actually identify. We can first cut out the entire plasticity training problem into two subproblems. One focus on training the elasticity. Another part is to use the elasticity model to find out where does the elastic response and the plastic response departure from each other, and so finding out where is the initial yielding point. The data we use is polycrystal data that, and this is actually one of the results that we obtained from the initial yield to the plasticity. One thing that are actually interesting we can see here is that traditionally the plasticity model would actually confine us to simple kinematic in the geometric, in the principal stress space or in the stress space, where we either have kinematic hardening, which means that the U surface are moving, but then keeping the same shape, isotropic hardening, where the particle are enlarging, or actually other hardening like rotations or actually frictional hardening. But here in this particular case, the hardening law is actually completely determined by computer, and that can actually deform. We can actually deform the U surface in any way, provided it accepts the physical constraint. So the idea is the following. We may start with a very simple shape, like we assume a circle, and then we actually keep exploring the data and then keep refining the shape. The same idea coming from maybe in a children book, we have different point, or we can have a different point in the parametric space that we represent different stress path. And then our goal is to try to link it and then create a smooth space. The data that we generate, use as a database, is actually generated from an FFT solver, in which we run different simulations in the piping, loading different paths, and then we try to come, and then we actually generate a microstructure that actually have different orientations. Each individual particle have a FFT, FCC crystal plasticity system, and then from that we can generate a very general anisotropic plasticity model. So one of the major ingredients central to the idea is that we are not going to use any handcraft U surface. Instead, we are going to combine the idea of U surface and level set problem into one, meaning that we consider that when the plasticity is involved, the U surface is involved in a specific way so that it remains sign distance functions. If you know the basic about the level set theory, sign distance function is a specific implicit functions where at the interface the sign distance functions equal to 0, and then in the interior and the exterior it actually become negative and positive, but then it has actually a unique gradient, which means that the norm of the gradient is actually equal to 1. So with that in mind, we can actually use it exploring the data by actually loading the material beyond the plasticity, and then obtain the new data point that have a new different isoplastic data, and then using that point to actually see how does the plasticity model evolve. And then that would actually, once we collect enough data point in the parametric space, we can form a new U surface. And from that new U surface, we convert it into sign distance functions that would generate another data set that we have. And then we use that data set to actually find out what is the solutions of the Hamiltonian Jacobi problem that are actually evolving the level set using the in the principal stress directions and also in the accumulated plastic domain, so that we can actually project the plasticity problem as a level set problem. And one important advantage is that through this training, we can actually generate a very general plasticity model that is not bound to any specific type of hardening. It could be completely general. And on the other hand, we can easily enforce the thermodynamic consistency by enforcing the convexity of the material. So here, for example, you can clearly see that if I put 2 points in the U surface, and if I actually somehow draw a straight line, then elastic respond again, then it already violate the Juger's postulate. So we can use the classical law that we have to help us make better model. So this is actually the detail of the training. Again, the whole plasticity model now is break down into multiple smaller problems. We first train the elasticity model first, and in a moment, I'm going to talk about the detail about the machine learning. But one thing that, and here we assume isotropic plasticity model, and hence everything is done in the principal stress directions. So in each time set, we know what is the tri-stress because we can actually generate direct numerical simulation that turn off the plasticity. And from the tri-stress, and by comparing the tri-stress and the current stress in the same string part, we can actually find out what is the plastic multiplier and then where is the plastic flow. And that will give us one data point for the training. By visiting the entire the piping for isotropic for isochoric plastic flow problem, we can actually link it together to form the U surface. But we can also, from the plasticity, find out what is the plastic flow. And what we actually need to do if we want to do isotropic elasticity is to introduce a new learning problem where we are trying to predict the U surface, not only feeding the U function value, but actually have the right stress gradient and have the right principal stress and have the right stress gradient of the U function such that we get the right U surface. The training data that we have is actually not exactly the experimental data, but the experimental data the yielding data converts into a level set. You can see another benefit of using the level set is that if I just use the plasticity data, the entire plasticity model would only take advantage of the red curve that only have one boundary, and then we need to actually come up with an implicit function for the entire parametric space that can lead to the loss of the stability. But with the level set data, we generate additional data that help us regularizing the performance of the U surface to remain such that the response is actually more stable. So this is one example. So now the plasticity problem becomes simply a level set problem. And we can see that in this case, we generate an ad hoc data set that converge a non-convex problem into just a Juker-Prager problem. And you can, one thing you want to pay attention is the capacity of the hardening that can be afforded by this model, where we can actually essentially generate any type of U functions that fulfill the physical law, but we are not so constrained by having a black box model that we cannot analyze whether the material fulfill the constraint. Another important thing that we find is that enforcing the U functions as a sign distance function actually provide a lot of benefit on the training. You can see the purple curve that are used to training the U functions. And in this case, we can see that for multiple different material, introducing the sign distance functions actually due to some performance, actually lead to more consistent learning rate performance. And in both cases, the training actually yield pretty good results. One thing that advantageous also for this method is that the implementation is very simple. So this is a classical principal string implementation of arbitrary isotropic hyper-elasticity plasticity model. You can see that the only thing that we need to change is actually the solver, the local solve, where we find out what is the yield surface, because we no longer have mathematical expression of the Harding law. We simply need to check whether the yield function equal to 0. We simply need to enforcing that using the machine learning algorithm, and then you can implement in a return mapping that guaranteed the smoothness. One thing that the important ingredient I would also like to talk about is that when we try to predict a constitutive response, let's say from strain to stress, oftentimes it becomes not so easy to put it into the finite element, in particular the implicit finite element. One of the issues is the lack of smoothness or the consistency between the stress predictions and the tangent prediction and also the energy predictions. So the goal of this method is actually not directly predicting the stress and strain, but actually trying to predict the energy functional and the yield functions that we use the gradient of it to actually yield the response. The detail to do it is the following. We need to customize our active function. So this is a typical ReLU activation function that are used for feed-forward neural network. As you can see here, this is actually not suitable for our purpose, because if we predict the energy functional, let's say store elastic energy functional, the first derivative gives us the stress, the second one gives us the tangent. But if you're actually doing this using this activation function, you will get a 0 for your second derivative. So we find different ways. One way to doing it is to use a different activation functions. But what we actually did here is to introduce the nonlinearity by actually adding a multiplier layer that actually can help us control the nonlinearity. Basically, the output is just the two. Basically, the neuron just propagated the result that we multiply together to increase the degree of continuity of the results. This is a very simple trick. Now again, if you actually work on if you're actually trying to minimizing the L2 norm, what we get is basically the minimizing the inner product, the square root of the inner product or the inner product itself. What we are trying to do here is to introduce higher order training, so we can leverage the data a little bit more efficiently. If you have one data point that gives us the stress, and we also have the tangent and the energy functional, the new L2 norm loss functions can take advantage of not only the stress data, but the energy data and the tangent data. So that gives us more chance to regulate the data and lead to more smooth results. We can see the comparisons. Actually, the interesting thing is that if we use the H2 loss functions, it performs better even when we measure the error using the L2 norm. And this is quite consistent in the sense that with the higher order norm, it actually helps us simply perform better even in order, not only on the gradient and on the second derivative, but also in the original data itself. So you can see here that this is actually the L2 loss, but this is actually on the L2. But the important, and this is actually the corresponding H2 training. We can see that the curve looks similar, but if you look at the y-axis, they are of different units. This is 10 to minus 8, this is 10 to minus 6. So you can also see that this is actually a very important point, is that if we predict the energy functional, we can get something look really accurate. But as we take the first derivative, we can see quite a bit of the discrepancy. So the higher order is actually working, would actually help us regularizing the problem better. And again, the data can also allow us to check the convexity, which is not something that previously available. In the elasticity case, you simply can compute the Hertzian matrix. and then we can get and then that would be the tangential elastic operator, and from that we can actually check whether it's positive definite. So this is actually more example on the simple training. Again, the goal is to see whether the level set can unify all the different parasiticity model into one training program. And if we can doing it in one meta modeling training program for different data, we can automatically get different hardening. So we have already presented this result, but this is actually all the other results. We can think about it in the classical way of doing kinematic hardening. We need the backstress to control this changing. In the isotropic hardening, we need some hardening parameter, frictional rotation. But here, the driver of the revolutions of the parasiticity is the neural network itself, and the neural network is actually trained with a higher order prediction in mind, so that the resultant isopathic pattern is actually sufficiently smooth and suitable for putting it in finite element. So this is actually another comparison in which this is actually on a soil material. You can see that it has some complex constitutive response that initially it looks like a chemplay model, but it has a little bit of kinematic hardening that are actually evolving. But notice one thing is that the loading paths are actually very different in these three cases, and the result is actually still very robust. You can see the hardening in this case and this case, and the softening in the other case. So you can tell that with the elastopathic framework that are again embedded into the learning problem, the result is more robust. We can go to the next slide. This is actually an example, perhaps not super fair, is that we just have a monolithic loading without any unloading data, and then we actually fit it into the gate recurrent neural network, and then we see what happened, and we compare with our model. If you never have that unseen pattern that involve unloading, of course, then no recurrent neural network can predict a very good unloading, because basically when you try to train those data, it will try to go up, and then when it's unloading, there's no way the neural network can figure out if there's unloading, and it will just trying to go back. And the worst is that sometimes you can lead to this unstable pattern that are actually quite often happening. This is actually more results. Okay, so the model that we are using, the levels of hardening, is actually the green one, and this is actually all the other possible back box neural network that we can find out. 1D convolution is actually the pink one, and then the gate recurrent neural network, and then the direct FFT benchmark is actually in the red sign. You can see that except in this small discrepancy, the model, the level set hardening actually perform really well, not just in terms of accuracy, but it's very robust. You won't see those funny patterns that actually happen in the stepwise training, and you also won't see the unrealistic nonlinearity that actually happen in the gate recurrent network or the convolutional neural network. You simply get the pattern. The reason is that we are not directly predicting the stress strength, but predicting a yield functions where we can easily control the smoothness very implicitly. So this is actually another simulation we introduced. This is actually a polycrystal simulations in which we run FFT finite element, and then we compare it with the neural network model, and then the results on the top are the FFT finite element, and then the bottom are actually the level set hardening model. So you can again seeing the revolution of it. I think I still have 5 minutes. So, but the important thing that I would like to point out is that so the model is actually very robust and not surprisingly have a sufficiently smooth result that actually can be put into the finite element without a lot of struggle on finding the tangent. Basically, I was saying that generating the tangent is actually almost free here, because we can simply using the TensorFlow automatic differentiations to get the tangent, and not only that, the tangent that we obtain is also verified with the higher order training. Okay, so this is actually another relay work about the future. In the future, what we like to do is to generate a better exploration problem. We want to actually constitute a game-like environment where we start with very little data, and then we would use the reinforcement learning to actually keep refining the model as we're exploring and generate more data. So this is one recent work that actually published with my former student Kun Wong and my colleagues, Professor Quen Du from Applied Math department, in which we use a non-cooperative game theory to actually not only try to calibrate the model, but try to attack the model at the same time. So we can see that initially the attack is actually pretty random, but at the end of the game, we are trying to, the model can actually spot the strength of the model and also find out the weakness. So the attacker found out that in this particular case, the Juker blocker is not so good in the cyclic loading, but then the calibrator is actually found out that it's pretty good at calibrations. So we also have another work that my students are going to have a poster that are on model feed method. In a case where we have enough data and then we don't need a model, we can actually using data-driven approach that our previous speaker, Professor J.S. Chen, also talked a little bit about, but extend it to the pole mechanics problem. So another work we don't really have time to go over today is the incorporate of the graph neural network. In particular, we are interested in knowing how does the revolutions of the graph, in this case, this is a DEM simulations, as the graph that represent the microstructure are evolving, how do we incorporate this information to make better model? So I'm always running out of time, and I know that this is a long day, so I'll just conclude here. So the major idea that I would like to present here is that we try to combine the level set problem and plasticity problem into one. So they give us the right amount of the flexibility and generosity to actually find out, to constitute a learning problem for the plasticity model. Here, I would confess that I don't think I make a lot of progress in the machine learning aspect. We simply use a very simple technique like a sober training, but the idea is the following. Sometimes when we constitute the right learning problem, then most of the difficulty are already gone, and what we need to do, well, and then we can actually simply leverage the neural network or the deep learning much more efficiently. So this is actually kind of the realization we get at the end of it. So the serverless training is actually very important here because it provides the essential control on the shape and the form of the elasticity, energy functional, and the U surface. And then we can leverage the geometrical interpretation to check the thermodynamic constraint. And then another major goal of this work is to generate a very general mechanism that can generate any plasticity model. We don't have any damage here, but that may also be another next step. So I want to again acknowledge my colleagues and my funding provider that actually sponsor this research. I want to thank my student one more time for doing all the hard work. And I want to, again, promoting the next conference that will be at UC San Diego, organized by Professor Chen and also the Professor Liu that are giving the talk today. So thank you very much. I'll take any questions. Thank you.
Thanks very much, Steve. Impressive body of work, really comprehensive and wide-ranging. There are a couple of questions. Let me just read them out here. The first question is how one ensures conservation principles are being met by the trained plasticity model.
This is on Gauss's point. So we haven't enforced the balance of linear momentum or balance of mass. But for the other thing like thermodynamics, because in this model we have the U surface, we can find out what is the partition of the elasticity, elastic strength and plastic strength. So we can check, for example, Juker's oscillate to see whether it actually see whether it's thermodynamic consistent. Another advantage is that we can actually use some of the geometrical interpretation to check the constraint, for example, convexity of the U surface. rather than actually ad hocly checking everywhere. We can simply check whether at any point it lost the complexity.
Great. So a couple of other questions too, also about your choice of activation functions. Anything special about the quadratic activation over?
Yeah, we simply, I think this is actually a very common question that we got. We have something special for the activation functions. They are more than one possibility, but here we simply introduce a custom activation function that multiply the neural network together. So that way we guarantee that we can increase the continuity. And then of course, then the weight of the neural network that we have a different meaning right now. But there are other ways to do it. Another more direct way is to think about what is the activation functions that can take a loss of derivative, like a NERSC or zero infinite continuity system. But you may, but this is kind of like the basis. We need to know what kind of result we get when we take 2 or 3 derivative. So there are some customized choice that must be made in order to get the good results. For example, I won't want something that if I take a loss of derivative, I will get a loss of oscillations and stuff like that.
Cool. A couple of more questions. Maybe I'll skip to the last one here. Could you say, can you say a few things about the graph convolutional networks?
Yeah, I can talk a little bit about that. I only have one slide, so this is actually pretty. But I have another slide that I gave during the summer in the USA ACCM, and it's still online right now. So I can post a link in the discussion board. But the long story short is that we do the convolutional neural network, but not on the Euclidean space on the graph. The reason is that we want to study polycrystal, and this naturally lead to a very natural wave graph that we can use. We can simply put each grain of the polycrystal as a node and connecting with the edge, and then we can assign meaning to the particle. And one of the advantages is that you start with data that are much smaller and already have some filtering capacity. For example, if the micro CD image have some ring amplifier or some error, the resulting graph won't have any of that because you already filter out those high frequency behavior. The result of it, because we are running out of time, I'm not using it as a skill, but really we should go. But it's actually can be found in this paper. We use a spectral graph theory that basically use the graph Laplacian, and then from that we deduct the encode feature vector. There are other ways that can use a spatial method. We're still thinking about which way is to go, but I think that the spectral have some advantage in generate a very good lattice space.
Thanks. I think there's just one more about anything special about tricks for initializing the response surfaces. Sorry. Did you get the last question, Steve? Any special tricks for initializing the response surfaces?
Oh yeah, and any way to doing it. Let me go back to that slide. Sorry, I did not get the. So the initial surface, basically, some of it is written in the loss functions. You control the shape by controlling whether it has convexity, but basically, we don't know the initial shape. So if you only visit one data point, the best you can do is assume it's a circle. So this is also a strategy that we can talk about, is how to visit, given a finite chance of visiting the different stress point, what is the least amount of visit you can get to get the best shape. So right now we basically just visit everywhere evenly. So if you know what I mean. So in this case, we work on isochoric flow. So the positivity only need to occur from the piping. This is like most efficient. And then we just visit everywhere equally until we find the shape. But that lead to another question, is that you can actually leverage the symmetry to help you find a better visiting program, so that you can get the shape much faster instead of visiting everywhere. Like here, we take advantage of that. The hydrostatic axis basically have no change, so we just focus on all the explorations on the piping. But you can think about other symmetry. the more general the problem is, the more data you require to get the shape initial use service correct, and you need more data evolving as well. But I think, sorry, 1 more minute. It's that. But I guess the important thing is that in that level set revolution is that if you don't have data, you can always assume the simplest mechanism to begin with. And as you have more data, you can converge it into more complex mechanism that can guarantee you get some sort of robust result rather than simply giving up on that parametric space that have no data.
Cool. Yeah. So that's great. Thanks, Steve. I think we are well past our time, and I think that's it for questions.
Yeah.
I have some more, but I'll just ask you separately or on the chat or something.
I'm sorry that I enforced the time constraint on everyone except myself.
Yeah, that's fine. I think we distributed the time almost pretty much evenly. So thanks, Steve. Thanks, JS, and thanks, Emma. Thanks everybody who spoke today. We should also remember that there is a poster session associated with this with the mechanical and civil track. You'll be able to see it if you navigate to through the conference website. You'll be able to come to the posters and see there are a number of really very high quality posters. So I do encourage all of you to go and take a look at them. And other than that, we will regroup tomorrow. I think the first session tomorrow is at 12:30. 12:20. Okay, great. Thanks again, everybody, and we'll catch up tomorrow.
Thank you, everyone. Thank you, Chris.
Thanks, everyone. Bye.
Yeah, bye.